Okay, so we're going to dive into a technology that's, well, it's not just another upgrade. This is a massive shift, a real phase change for civilization. It's about finally moving past perfecting our digital world and getting our hands dirty mastering the physical one. Let's jump right in.
And this quote, man, it just hits the nail on the head, right? It perfectly captures this weird spot we're in. When it comes to the digital world, the world of bits, we're basically wizards, building the future at an incredible pace. But in the world of atoms, actual stuff, it's kind of shocking how little has fundamentally changed.
Yeah, that banging rocks together part, it's a story of stagnation. And to really get why this new tech is such a revolution, we first have to wrap our heads around this plateau we've been stuck on in the physical world for, like, the last half-century.
I mean, seriously, think about it. You've probably flown on a Boeing 737, right? It's one of the most common planes out there. Well, its basic airframe design, that's from the 1960s. Sure, we've slapped on new engines, better software, all that jazz, but the core physical structure, the fundamental way it flies, it hasn't really changed. And it's the exact same story down here on the ground. The engine in most of our cars, it's just a souped-up, super refined version of a technology from the Victorian era. We're getting really, really good at polishing old ideas, making them more efficient, but we're not inventing anything truly new. Heck, even our giant skyscrapers, we build them by pouring concrete. You know who'd recognize that technique? The ancient Romans. They'd look at our construction sites and go, yep, looks familiar. We've basically hit a wall, a physical limit in how we build our world. Now, this isn't because we've run out of ideas or imagination, not at all. It's because we've slammed right into the physical limits of our methods. For centuries, manufacturing has been about heat and beat. You melt stuff down, you hammer it into shape. But that whole process is chained to the laws of thermodynamics. You can only get something so hot before it just falls apart. So what if you could just sidestep those limits entirely? What if you could shape materials with incredible precision without melting them? This is where things get really exciting. This is where we step into what's being called the quantum forge, a completely new way of making things, powered by two amazing tools. Tool number one is a petawatt laser, and that number you're seeing, yeah, that's not a typo. We're talking 1 quadrillion watts. For just a tiny fraction of a second, this laser focuses more raw power on a single point than every power plant on Earth combined. I mean, it's an amount of energy that's just, it's hard to even wrap your mind around. Okay, so how on earth do you wield that kind of power without instantly vaporizing your own equipment? Well, that's where a Nobel Prize-winning idea comes in. The gist is, you take a little pulse of light, you stretch it out in time, kind of like an accordion, which makes it safe to pump a ton of energy into it. Then, at the very last second, you slam it all back together right at the target. It's an absolutely brilliant solution. And the result of this trick is where the real magic happens. See, a normal powerful laser just melts metal, it's messy, it warps the material, it creates weak spots, but this petawatt laser pulse is so unbelievably fast that the atoms don't even have time to get hot. They just blink out of existence. It's called cold ablation. It's the difference between trying to sculpt with a sledgehammer versus a scalpel that can carve individual atoms. All right, so if that laser is our atomic-level scalpel, we need something to hold the material, right? That's the other half of this equation, 6D fabrication. Now, the first 5 dimensions are pretty easy to picture. You've got your standard X, Y, and Z axes, up, down, left, right. Then you add rotation and tilt. This just means the machine can build something from literally any angle, which gets rid of those weak layers you see in normal 3D printing. But it's that 6th dimension. That's the real breakthrough.
Yeah, this is the absolute game changer. The machine isn't just blindly following a digital blueprint anymore. It's actually sensing the material as it's being laid down, and it's using that insane laser to tweak its properties in real time, one tiny little 3D pixel, or voxel, at a time. Honestly, calling it printing doesn't even do it justice. It's closer to, I don't know, controlled, accelerated evolution for materials.
Okay, so we've got an atomic scalpel and an intelligent 6-dimensional building platform, the quantum forge. The big question is, what can you actually do with it? Well, it turns out you can start tackling some problems that, until now, have been completely impossible to solve. Let's talk about clean energy. For decades, the holy grail has been nuclear fusion. And a big part of that challenge is taking a tiny little fuel pellet and crushing it with unbelievable force. Here's the catch. If that pellet isn't perfectly, flawlessly spherical, the whole thing fizzles out. It's a ridiculously hard geometry problem. Well, the quantum forge just solves it.
It can print these little fuel targets and then use that precision laser to polish them, shaving off any tiny imperfection atom by atom until you have a sphere that's more perfect than anything else in the universe. And it can crank these out by the thousands every hour. Suddenly, a commercial fusion power plant starts to look a whole lot more realistic.
Okay, here's another impossible problem: hypersonic flight. The big challenge isn't just going fast, it's the insane heat. When you're screaming through the air at Mach 5, the air friction turns the atmosphere around you into a ball of superheated plasma. It'll melt pretty much any material we have, and it completely blacks out all radio communication. You're basically flying blind inside a star.
So what's the solution? You print materials that shouldn't exist. You use the forge to build a wing with millions of microscopic channels inside it, so it can literally sweat coolant to stay intact. Or you print an antenna with a surface so precisely structured that it becomes transparent to that plasma, letting you communicate right through the fire. This is a complete paradigm shift for defense, for space exploration, you name it.
Okay, let's bring it even closer to home, inside our own bodies. Things like titanium hip replacements are amazing, but they're not perfect. Our bodies can see them as smooth, foreign invaders and try to reject them. And worse, that smooth surface can become a perfect breeding ground for nasty bacteria.
With the quantum forge, you could print an implant that has the exact same porous structure as a patient's own bone, so the body just welcomes it and bone grows right into it. But here's the really wild part. You can also etch the surface with tiny microscopic spikes. They're too small to harm our own cells, but when a bacterium lands on it, pop, it gets physically ripped apart. It's like a mechanical antibiotic built right into the implant.
So all of this, it leads to a number that just sounds fake. A quadrillion-dollar market. I know, right? How can one single technology possibly be worth more than the entire global economy as it exists today? It sounds nuts.
The way to understand it is through a concept called notional value. The idea isn't that someone's going to sell $1 quadrillion worth of these printers. No, it's about the total value of all the new industries this technology makes possible from scratch. Entire economies that literally could not exist before this.
And what are we talking about here? We're talking about the fusion energy economy, with its promise of nearly limitless clean power. We're talking about an asteroid mining economy, because now we can build the exotic materials needed for those ships. We're talking about a human longevity economy, built on things like those perfect bacteria-shredding implants. Any one of these, on its own, would completely reshape our world. Now, look, let's be realistic. This future isn't going to happen overnight, and it's not a sure thing. There are massive hurdles. The amount of energy these lasers chew through is staggering. The supply chains for the exotic materials you'd need are tricky, to say the least. And just imagine the regulatory nightmare of getting all this approved. These are serious, serious challenges. But if we can solve those problems, the takeaway is just undeniable. That long period of stagnation, the era where our physical world just couldn't catch up to our digital ambitions, that's coming to an end. We are finally learning how to shape our world with intention, atom by perfect atom.